Good day, everyone. Today, we will discuss quantifiers in the principle of mathematical induction, or also known as PMI in abstract algebra. These concepts are important because they help us express mathematical statements clearly and prove whether they are true or false. In higher mathematics, especially in abstract algebra, we focus more on proving properties rather than simply solving equations. In this presentation, we will first explain quantifiers, their types, how to translate statements into symbols, and how to properly negate them. After that, we will discuss the principle of mathematical induction and present examples step by step. Let us begin with quantifiers.
So what is quantifiers? Quantifiers are the symbols used in mathematics and logic to indicate how many elements in a set satisfy a certain condition. There are two main types of quantifiers, which are the universal quantifier and the existential quantifier. So first, let us discuss what is universal quantifier. The universal quantifier uses the symbol of inverted A, which means for all or for every. It states that a condition is true for all elements in a given set. So, our first example, here is the statement. Every real number added to 0 is equal to itself. So, symbolically, it is for all x is an element of real numbers where x plus 0 is equal to x. This means that for every real number x, adding 0 does not change its value. Now, let's have another example. So, statement is for every integer x where x squared is not equal to 0. So, symbolically, for all x is an element of integers where x squared is not equal to 0. This tells us that the statement claims all integers squared are not equal to 0.
Next, we have the existential quantifier. The existential quantifier uses symbols inverted E, which means there exists. It tells us that at least one element in the set satisfies the given condition. We have example. This statement, there exists an integer whose square is equal to 9. In symbols, there exists an x which is an element of z such that x squared is equal to 9. This statement is true because 3 and negative 3 satisfy the conditions. Do you want more example? Okay, so we have another one. This statement, there exists a real number whose square is 2. In symbols, there exists an x which is an element of real number such that x squared is equal to 2. This is true because square root of 2 is a real number. So let's have another example. We have this statement. There exists an identity element in the group G. Symbolically, there exists an E which is an element of G such that A star E is equal to A. For all A is an element of G. This means that there is an identity element in the group that does not change any element under the operation.
Now, let's explore how to negate the universal quantifier. The negation of the universal quantifier becomes an existential quantifier. So the general rule is the negation of for all x where p of x becomes this exists where x such that not p of x. So symbolically, the negation of for all x where p of x is equivalent to there exists of x where p of x is not true. When negating, we must also change the mathematical operations into their opposites. For example, greater than becomes less than or equal to. Less than becomes greater than or equal to. Equal becomes not equal. And becomes or becomes and. For example, here is the statement. All real numbers are positive. Symbolically, for all x is an element of real numbers where x is greater than 0. So how to negate? So the negation of there exists of x where are element of real number such that x is less than or equal to 0. Another example, for every integer x where x squared is not equal to 0. So how to negate? So the negation is there exists an element of integers such that x squared is equal to 0. Notice that for every change into there exists, and the condition was reversed.
And now, let's move to the negation of an existential quantifier. The negation of an existential quantifier becomes a universal quantifier. So we have the general rule. The negation of there exists an x such that px becomes for all x, px is not true. Symbolically, the negation of there exists an x where px is true is equivalent to for all x, px is not true. And we have an example. So this statement, there exists a real number less than 0. So in symbols, it becomes there exists an x which is an element of real number such that x is less than 0. So its negation will look like this. For all x, an element of real number such that x is greater than or equal to 0. So let's have another example. So we have this. There exists an integer x such that x is greater than 2 and x is less than 5. So its negation will look like this. For all x, an element of integer such that x is less than or equal to 2 or x is greater than or equal to 5. Notice that an and changed into or.
And now, let us move to the principle of mathematical induction, or let us call this PMI. So PMI is a proof method used to prove statements that are true for all natural numbers. So it has two important steps. So first, we have the base case. So the base case proves that the statement is true for the first value. So we have here n is equal to 1. So the next step we have is the inductive step. So we assume that it is true for n is equal to k, then prove it is true for n is equal to k plus 1. So if both steps are satisfied, then the statement is true for all natural numbers. And now we have example number 1. So prove that 1 plus 2 plus 3 and so on plus n is equal to n times n plus 1 over 2. So now let's proceed to step 1, which is the base case. So we have here n is equal to 1. So the left side of our equation we have 1. So the right side will become 1 times 1 plus 1, which is 2, then over 2, which is equal to 1. So both sides are equal. So the base case is true. So next we have step 2, which is the inductive hypothesis. So in this step, we assume that the formula is true for n is equal to k. So we have 1 plus 2 and so on plus k is equal to k times k plus 1 over 2. So next step, add k plus 1. So we have k plus 1 over 2 plus k plus 1. So next thing we do is we factor this equation. So now the result after factoring the equation will become like this. We have the k plus 1 or the quantity of k plus 1 multiplied by the quantity of k over 2 plus 1. So the next step we do is that we are going to simplify this equation. So the simplified form of this equation will become the quantity of k plus 1 multiplied by the quantity of k plus 2 over 2. So this matches the formula for n is equal to k plus 1. So therefore, the statement is true for all natural numbers. So to further deepen your understanding, let us have another example.
So now, let's proceed to example 2. So prove that 2 raised to n is greater than or equal to n plus 1 for all n is greater than or equal to 1. So in base case, 2 raised to 1 is equal to 2. 1 plus 1 is equal to 2. So this means that this is true. So in inductive hypothesis, assume that 2 raised to k is greater than or equal to k plus 1. So now let's proceed to the inductive steps. So first, 2k plus raised to k plus 1 is equal to 2 times 2 raised to k is greater than or equal to 2 times quantity of k plus 1. So now let's check. So 2k plus 2 is greater than or equal to k plus 1. So next, we will simplify. So we have here k is greater than or equal to 0. So since k is greater than or equal to 1, so the statement is true. So to summarize, quantifiers allow us to write mathematical statements clearly and precisely. The universal quantifiers refers to all elements, while the existential quantifiers refer to at least one element. We also learned how to properly negate quantifiers statement.
Finally, we apply the principle of mathematical induction to prove statements involving natural numbers. These concepts are essential in abstract algebra because proofs are the foundation of higher mathematics. And that concludes our tutorial. See you in our next session. Bye!